will be connected to a directional Yagi, and we will be taking the data that we receive from the transmitting LoRa and plotting it onto the maps and the 3D plot that you see here. This will enable us to better understand and better predict the landing position of the launch vehicle. And so some significant failure modes that we don't expect to see due to our mitigation, but would like to bring up. One of the most dangerous things is a battery explosion. So when working with LiPo batteries, so lithium poly-ion batteries, you have to be careful when you're both charging and discharging. Doing either too far can damage the battery. A battery explosion could cause damage to the rocket and could cause premature ejection. And it's mitigated through utilizing batteries that are large enough that they won't discharge to a damaging point, and also a charger that has the ability to stop charging once they're fully charged. The other is a short circuit, which could cause a fire inside the rocket. We'll be mitigating this through the utilization of vibration testing. Next slide. Now I'd like to introduce the Controlled Landing Mechanism Subteam Lead, Brian Zhang.
Hi, my name is Brian Zhang. I'm the subteam lead of the Controlled Landing Mechanism, or CLM, which is this year's primary payload. So starting from the top, the CLM consists of a recovery mechanism, which houses two parachutes, a main parachute in the shape of a cross, which will be explained in a later slide, as well as a drogue. Just below the parachutes is the camera housing, which consists of two cameras, and will use a clear section of polycarbonate to see out of. Finally, the legs mechanism consists of 4 legs, with all 18 inches long, which will be deployed at apogee. Altogether, the CLM is 22 inches in height and about 10 pounds. So the main component of the recovery mechanism is a cross parachute, which consists of 5 squares, each 28.9 inches by 28.9 inches, which results in a surface area of 29.05 feet squared. By manipulating the geometry of the shroud lines, CRT has forced the arms of the parachute to be at an angle, which puts a component of the drag force at an angular direction, which should cause spin. This should cause angular momentum, which should prevent pendular swing. Also, it should be noted that the main parachute, will be held closed by a Jolly-Logic chute release, which will keep the parachute closed until an altitude of 500 feet, at which point it will allow the parachute to open, and the drogue will be deployed at apogee as is standard. In the camera housing, there are 2 cameras, one Logitech C920 and also a Raspberry Pi camera board. These will be further explained in the target detection slides, but it is housed in a 12-inch section of clear polycarbonate. There is a 4-inch section of coupler at the top, as well as a 4-inch section of coupler at the bottom, which leaves 4 inches of unobstructed clear airframe for which the cameras can look out of. The images will be taken on ascent because CRT believes that there is more likelihood that the cameras will be oriented such that the full field of view is in sight. So the legs mechanism consists of 4 legs made out of polycarbonate, each 3/16 inches thick, 1 inch wide, as well as 18 inches long. They will be deployed by elastic straps, which will pull the legs from a stow position into the normal perpendicular position at apogee. They will be allowed to rotate independently through a rotational bearing mechanism, as is shown in the second diagram, which consists of 2 bearings as well as a turntable. This should reduce the angular impulse experienced when the CLM lands by allowing the upright portion to spin independently of the legs. While the damper is shown in the diagram, and it is explained in PDR, it has since been removed. So the 2 major requirements outlined by NASA are that the CLM must house a camera section and land upright. This will be accomplished by the aforementioned clear polycarbonate section and cameras, as well as the legs. It must also not exceed the kinetic energy limit of 75 foot-pounds, which will be accomplished by deploying 2 parachutes, the drogue and the main. Some team-derived requirements include that CRT must provide proof that the CLM lands upright, which will be facilitated by the ground crew. The legs must also actuate from the stow position to the perpendicular position, which will be accomplished by the elastic deployment straps. And also, all the components must be able to withstand the stresses both at launch and at landing. So the two significant failure modes that CRT is concerned about are failure of the parachute and failure of the legs. If the parachute does not deploy, either because the nose cone fails to eject or because the jolly logic malfunctions, then the CLT is in free fall, which is obviously not conducive to upright landing and also poses a significant safety concern. If the parachutes deploy too early, then the CLM may drift too far and may exceed the maximum drift limit of 2,500 feet. If the legs break, then the CLM may not have enough support to land on, and even if they don't break, then the CLM may be at an angle such that that is not conducive to upright landing. Both of these will be mitigated by drop testing, subscale and full-scale launches, as well as ground testing. I would now like to introduce Fred Kummer, the sub-team lead of the target detection system.
Hi, I'm Fred Kummer. I'm leading the team designing the target detection system. So for the mission requirements, the NASA SL outlined that we need to design an onboard camera system to identify and differentiate between three randomly placed targets on the launch field, as well as analyze the images in real time with a custom software package on board the launch vehicle. The team has also derived some requirements of their own, stating we need to track the state of the launch vehicle throughout its flight and recovery, meaning we need to know when it's launched, when it's on ascent, when it's on descent, when it's landed, and that we need to store a couple of images into a secondary backup storage for easy recovery and extra redundancy. It's just a summary of the system. We've taken a modular design approach, breaking it down into 7 independent modules that work through predefined interfaces. Each of them will be covered more in the following slides. There's the image processing computer, camera system, state control module, the sensor module, backup image storage, and the power distribution module. So to start with the image processing computer, actually analyzes and processes the image that come from the camera system and stores them. It decides when to take pictures based on the output of the state control module, which we'll describe a little more later. Currently we're using a Raspberry Pi 2 Model B. This uses a full Linux operating system and has significantly more power than sort of traditional microcontrollers we used in the past, which is better suited to the highly intensive computational task of the image processing. And then here's just a breakdown of the software architecture we're using for our custom software package. We've taken a modular design approach again, breaking into various different modules for photo capture, the actual processing of the image, overlaying it with verification criteria. So we're making use of the OpenCV image processing library for this. It really simplifies the task of image processing by providing us with a lot of pre-made code and functions that do a lot for us, and it's already had a lot of blowback when we're using Raspberry Pi. Taking this modular approach helps us separate things out for easier design and integration. And then under the camera system, we're using 2 different cameras. We're using a Raspberry Pi camera module designed specifically for this board and the Logitech C920. Notice that the Raspberry Pi camera module has higher native resolution, so ideally we'd be able to use 2 of them. Unfortunately, due to driver issues, we're unable to use 2 of them with a single Raspberry Pi, so we've separated into a USB webcam and a Raspberry Pi camera module. But both have resolutions that we believe are high enough to accurately capture the targets and have wide field of view to capture most of the pictures. And the state control module takes the output from the sensor module and uses it to determine what the optimal times would be for the image processing computer to actually take the pictures. This is meant to just lessen the computational load on the image processing computer, since analyzing images is already such a difficult task and we have limited processing power. We're going to be using an 18 mega 328P as the primary MCU to receive, analyze sensor data, and track the state of the flight. It's very low power, which allows it to sit for a long time on the pad without much trouble. And also we have past experience with the 18 mega 328P, making design and prototyping much simpler. Then there's the sensor module. It's going to detect acceleration and altitude using an accelerometer and an altimeter, and output that information to the state control module. The accelerometer is used to detect launch and landing, and the altimeter is used to track the state of the flight that it's currently in, so ascent versus descent. And this is going to be fed to the state control module as well as the image processing computer to make analysis easier. Then the power distribution module just distributes and regulates power to all the other modules to simplify their design so they don't have to concern themselves with how exactly they'll be powered and protection against overcurrent and voltage. So it interfaces with every other module and provides them with exactly what they need and protection. It also includes power control to allow the state control module to turn off the image processing computer and sensor module after landing to save power for recovery. Some significant significant failure modes, one of the most important would be damage to electronics during launch, where the high acceleration of the launch possibly damages important components or tears out connectors between the computer and other things. And in that case, the system could be inoperable or damaged beyond all repair. So using printed circuit boards with low profile components is going to mitigate that failure mode, as well as locking connectors for everything on the image processing computer. And then another failure mode we've had trouble with in the past is file system disruption, where a hard landing could possibly eject the SD card holding the operating system from the image processing computer, which often corrupts the file system and makes all data on there inaccessible. So we could lose any images of verified targets that we have, or all sensor data we recorded. So we're going to mitigate this by including the backend storage module, which stores all the verified images and can be safely unmounted from the file system before landing, meaning it should be very difficult for it to become corrupted unless it's completely destroyed. So now I'm going to introduce Chris Fedors and Brian Johnson to explain the role control system.
Hi, my name is Brian Johnson. I'm the sub-team lead of the role control system.
I'm Chris Fedors. I'm the electrical sub-team lead of the role control system.
So the role control system is the secondary and unscored payload for our NASA SL. And the requirements laid out in the handbook for the role control challenge is that we need to induce a rolling moment for at least 2 rotations. And we'll be accomplishing this by using a fin flap system with flaps on the aft launch vehicle fins, which will deflect to induce that moment. The secondary requirement is that we induce a counter rolling moment to return to the original rotation rate measured at motor burnout. And we'll be using the same system to accomplish that by just deflecting the fins in the opposite direction to induce the opposite moment. And the third requirement is a proof of induced roll, and to do that we'll be recording gyroscopic sensor data, which we'll then examine upon landing to verify that the roll was successful. We also have some additional team-derived requirements which will help us accomplish these tasks. We're aiming to rotate at a rate of 1 hertz for those 2 rotations. We're also looking to create mechanically linked flaps, which we've already done in our design, and that's verified in our PDR. We also want our system to be fully removable from the launch vehicle, as was previously mentioned, and we've also verified that in our current design. We also want to successfully induce roll in wind tunnel testing prior to any full-scale launch. In addition, we want to complete no more than 2 induced rotations at that 1 hertz rotation rate. We also want our algorithm to run at a speed of at least 10 hertz and store all the logged data onto the MCU. This is a summary of the mechanical components of the RCS system. As you can see, there's a control surface on each of the 3 fins of the launch vehicle. These control surfaces are driven by a single motor servo higher up in the booster section. The motion from that servo will be transferred down to the fins by push rods, and again, these fins will all be mechanically linked by a gear assembly system. So this is the upper portion of the RCS, containing both the electronics enclosure and the bevel gear assembly. The electronics enclosure houses all of our electrical components, including our servo, any PCBs, and sensors. The bevel gear assembly, which you can also see in the second figure, transfers the rotational motion from the servo to the push rods via lever arms here. And again, the gear from the servo is mechanically linking all 3 gears so that all 3 flaps deflect by the same amount. Here is the fin flap assembly. As you can see, we're using that same lever arm push rod system to accept the motion from higher up above in the bevel gear assembly and convert that back into rotational motion to deflect the fins. And these fins will be attached by a shaft on this end by a sleeve bearing, and on the booster section end by a ball bearing, which would be embedded inside the booster. And this is just a little bit more detail on that fin flap fin interface. again, you can see